Who has heard from anybody who's taken this class before, including maybe honors who's already made it through, that this is a hard section? Okay, there you go. And that was really quick, so some of you haven't even talked to other people, or you're just maybe not friends of people that have taken the class, or they haven't talked about it before. Vectors can be brutal, but to be honest, this stuff that we're going to cover today before the word problems, it's not that bad, number one. And number two, every year I try to make it a little bit more understandable and a little bit less pressure as far as having to like totally understand everything. Like for instance, what we've covered so far. Here's what I expect you to know about, well, a non-working smartboard. Cool, that's fun. Hi. Here's what I expect you to know about this picture. Number one, what does the arrow mean?
Vector. The point at it's the direction.
Okay, yeah, I heard different things, and all of them kind of meant it's going this way, right? It's a direction. What does it not mean? Yeah, it's not infinite. It's not array. It's not geometry. It doesn't go on forever. Okay, so far, who's like, yeah, I think I knew that from last week? 4 people. Sweet. It's going to be like chapel. I just shouldn't have anyone ever remember. Got it. Okay. So hopefully, let's do that. Hopefully, most of you knew that from last week. Question. If I was to ask you for an initial point, which one would be the initial? 2, because the arrow's at the other one. So if I was to ask you for the initial point, it would be this one, right? If I was to ask you for the terminal point, it would be the other one, right? There's, okay, only 2. And then you guys already said it doesn't go on forever. The arrow, I know it just got smaller when I made it bigger, but the arrow just means it's going that direction. What could this vector represent? It could just be a line. It could just be a length that went from there to there. It's like a little particle in the middle of space. Boom. What else could it be? I think it's roller coaster. What else could it stand for? Force. Good. It could be force. It could be length. It could be magnitude of anything. So it could be a magnitude of work or a magnitude of tension or tension. Sorry. Magnitude of tension. A magnitude of speed. It could measure all sorts of different quantities that some of you were like, maybe I've heard the word before, but I don't know. I haven't taken physics. Anyway, so it could represent all sorts of different things. But to be honest, from last week, that's about all I expected you to know. Does that sound good? Not too much pressure, right? So let's figure out how to do some of the problems and figure out what are they asking for over there. Magnitude, okay. It's like how much, right? Let's figure out how to not just do number 16, but hopefully get a lot farther in homework. But Daniel, go ahead, quick. What's up, then?
What are those lines? Like the 2 lines next to
these are the lines that we saw. Did we actually write them down on Friday, or is that just a thing that my imagination? Oh, I did write them down. The double lines are just a notation. It's kind of like double absolute values. They don't mean that, but they kind of do. The absolute value of a number is the how muchness of it, is the magnitude of it. Technically, it's the distance of the number on a number line. So how far is 4 from 0? 4. How far is negative 4 from 0? 4. It's just like what's the magnitude of the number. So these double lines, I think they're just kind of to keep them separate from absolute value, and these aren't numbers. So absolute value of this wouldn't make much sense because it's not a number. So it's vectors, or both of these are vectors. We use the double lines to signify magnitude. So you can think how much, but it doesn't work the same as an absolute value would just for normal numbers. Okay, kind of lengthy, but there you go. P.S. Last thing, we didn't actually name that vector over there. Let's do that. The last thing that you should have maybe remembered from last week. We could call this any lowercase letter. Give me one. Ready, set, go. I heard M first, but S was close behind. It could be vector M, but couldn't it also be vector... Uh-oh, now I need 2 letters. S and V. So I could do S and I could do V. That's no fun. I put them in alphabetical order. I just got rid of my point. That's okay. Let me do V and then S. Here's my question. How else could I name this point? SV or VS? Yes. Because it has to be from initial to terminal. Nice. Hey, we did get some stuff down last week, right? For a little bit, we're kind of like a science class. Just a little bit, but we gotta do some math. So here we go. If we're talking about vector RS, R being the beginning, S being the ending, R being the initial, S being the terminal. We could talk about him in terms of what we call his, ready? You guys see it over here? Components. Despicable Me, the little villain dude. Vector. It's a line segment with both direction and magnitude, right? That's the easiest way to describe a vector. It's not the easiest way to do math with a vector. I was asking a little bit earlier about vectors, and somebody mentioned geometry. It's like, yes, but to be honest, we're going to work our way around not having to use the law of cosines, law of sines. I'm going to solve the problem in a little bit with the law of sines and law of cosines. But this is the geometry way to do it. But we can technically avoid some of that geometry if we use components. So this is definitely in your best interest. If you want, you can put a little note. Components make everything easier with vectors, especially if you have more than two. If you think back to the roller coaster just for a second, there were little people in the cars at different positions on the track, especially talking about like a loop. And you could see all the forces in the car, on the people. Gravity was going down and the normal force was going up. And then off to the side were the vector diagrams where they had made a whole triangle, putting the vectors like going head to tail, and then the overall net force. That needs geometry. But if we can use components, things get better. But let me show you how components work. Let's say this point has, we could call it an XY. But guys, they can talk about order pairs with different letters than X and Y, especially when you have lots of different ones. So let me show you how the book talks about points in this section, at least. Doesn't mean every physics book out there would. But they could use lowercase s1, lowercase s2 to be the x and the y of the s point. And then little lowercase r1. You guys see a pattern, yeah? The x, y, they're just using the lowercase letter of the point. And then subscript 1 is the x, subscript 2 is the y. So what I could do is I could talk about r to s and that movement, that diagonal directed something, force, motion. I could talk about it with magnitude and direction. Where is it headed and how long is it? Or I could just say in terms of its horizontal change and its vertical change. And to do that, I would do its terminal x minus its initial x and its terminal y minus its initial y. I'm going to write right above it just because some of you might have gotten lost in with all the lowercase letters and the new notation. So what we're doing is we're doing terminal, where the arrow is, minus initial, and we're splitting it up into both horizontal component and vertical component. And specifically, you can think of it if it helps horizontal change and vertical change. And change in math, change in, and it's always a subtraction. So instead of talking about the diagonal directed motion or movement or force, in essence, what we're doing, and I can't really draw the arrow because we're not really talking about it in terms of vectors. We're just saying, hey, there's been a horizontal change and a vertical change. And it can get me there in, well, if I was moving in a much more convoluted way. Like, oh my goodness, if I want to get to in and out, just hop all the fences and, oh, maybe actually sometimes in life we have to move horizontally and vertically to get to some place that's diagonally away. Maybe there is some application to this. However, usually, like if we're up on the quad or up on the field, we want to get to someone across the way, we would just cut through the field, no big deal. I just go over and talk to them. But in life, sometimes you can't just go the diagonal way. Sometimes you have to go the horizontal, vertical way. Anyway, components basically say, hey, let's talk about, we can call this like an A and call this like a B. Let's talk about the components and how we can find those components. Is by subtracting terminal minus initial for x's and y's. And so even though this is the math to solve, can you guys on the other side just kind of show, okay, but then after you subtract, you get a number. And then after you subtract, you get a number. So this is how to get the A and how to get the B. At the end of the day, you can write a vector in terms of its components, an A and a B. Now, what are a lot of people going to think this is? Two numbers separated by a comma. They're going to be like, oh, it's a ordered pair, but what is not around it? It says parentheses are not around it. Now, intervals have parentheses, and they're not ordered pairs either. Okay, math has some different common things that are used, and you have to pay attention to the context to see what it means, right? But we have these little side carrots. Carrot. Proofreading. English. Whenever you have like a rough draft and someone's correcting it for you, can't they do this to be like an omitted word, right? Like, ooh, you left out this word, like put it in. That's a caret, true? Or in your calculator, can't this mean like to the power of? Just side caret, okay? They're like parentheses, they're like brackets, they're grouping symbols, but they're side carets. It can be like a, ooh, hey, components. But how could we find the magnitude, the how muchness of vector v, of vector r to s, either way, if we did know a and if we did know b? If the magnitude is the length, it's as easy as Pythagorean theorem, a squared plus b squared. Even though it's like, well, you could use the distance formula. Yeah, I suppose. But if you have the components, it's as easy as just a simple Pythagorean theorem. Once again, distance formula is Pythagorean. Oh my goodness, the first day of class, but either way. All that to say. So if we're over here, if they want me to find the component form of this vector, oh, they called him V. Oh, whatever. I called him M. Okay. If they want me to find the component form of this guy, apply what we just did, guys. So who's going to be his A or his horizontal component? His horizontal change. Close. Is it a positive 3 or a negative 3? Is it 2 minus negative 1 or negative 1 minus 2? Who's the terminal? The arrow guy. Who's the arrow guy? S. Aha. It's going to be negative 1 minus 2. That's the horizontal. I have to go terminal minus initial. And then it's going to be 4 minus 2. So then his components are as easy as negative 3, comma, 2. If it helps you, what does that mean in context of the problem? From the terminal to the initial, I have to go 3 left, and I have to go, wait a minute. Is that confusing? Even though we do terminal minus initial, the movement is actually initial to terminal. Now check it. 2 up and 3 left. Does that work? A positive 2 and then a negative 3. So I know it's terminal minus initial, but it's showing movement from initial to terminal. Aiden, what's that? Yes, you may. Understandable at the ground. Wait a minute, magnitude. We're not done yet. But once we have the components, what's magnitude as easy as? Yeah, a squared plus b squared. It's negative 3 squared. At this point, the signs don't truly matter. So even if you messed up the signs, you could still get the magnitude. We have 9 and 4 is 13. We can go back to algebra 1 and be like, hey, how do you simplify the radical? But isn't 13 a prime number? Okay, forget that. We're done. Dun, 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 dun. So what does that mean? In context of the problem, with this little vector, if I want to talk about his magnitude and his direction, well, actually, I don't know his direction besides it's like that. They didn't make me find some sort of weird, oh, that's awkward. He's like out in the middle of nowhere. I don't even know what his angle would be. Would it be like that? Or would I like measure it from there? Do I do like a bearing with his north? I don't know. Good thing they didn't ask me about his direction right now. But they did ask me about his components, so I subtracted the x's and subtracted the y's in the terminal minus initial fashion. It showed me the movement, the horizontal displacement and the vertical displacement, and then a quick Pythagorean theorem got me root 13. There's one thing we didn't get down here. We didn't fill in yet. A 0 vector is a vector that hasn't gone anywhere. He's technically just a point. He's kind of boring. He has no length. He has no horizontal or vertical displacement. His magnitude would be 0, even if you want to write that down. But a unit vector is one whose magnitude is 1. Now, let me just do a couple examples of unit vector. Just try to develop that for a bit. Question. What would be the magnitude of this guy? Yeah, 1. Because when I do a squared plus b squared, what's 1 squared plus 0? Square root of 1 is 1. What would be the magnitude of this guy? He'd be 1 too, right? What would be the magnitude of... Ooh, hold on, I have to think for a second on this one. Two and 1 all over root 5. Oh, that's mean. Oh, that's mean. Well, hold on. How did I find him? How did I figure out this was a unit vector too? Do you guys see that I wrote 2 and 1 first? What's the magnitude of a vector 2, 1? 5, because it's 2 squared plus 1 squared, right? 5. Wait, it's not 5, it's root 5, right? And what did I do to both of them? Well, I scaled it back. Yeah, I took my go over 2, go up 1. I took my vector 2, 1, and I scaled them back. So what was 2, I divided by root 5. What was 1, I divided by root 5. And what was root 5 will be divided by root 5. What's root 5 over 5? 1. Huh. There's something in there about a unit vector. Some of you might have gotten stuck on unit vector problems. We have a formula. It's coming. Hang in there. But for right now, that's just the idea. Let's keep going. Okay. So what do we do if they're expecting us to add, maybe subtract, maybe multiply vectors by numbers? I'm going to show you with the picture, and then I'm going to show you with components. Okay? I'm going to show you with the picture, then I'm going to show you with components. Up here, what if they want us, well, actually, we can kind of use what's over here. They want us to triple v in a second. So let's go ahead and take this and say, okay, what do we do if we triple v? So we have a vector v. Remember, you guys should be writing arrows on top of all these bold letters, right? That's a vector, 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 and then all these views. Vector, 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 vector. Way more than I needed, but anyway, that's the idea. Okay. If we were talking about multiplying a vector times 3, or times 2, or times 10, or times any scalar in physics, a scalar just means, technically means dimensionless value, a dimensionless number. There is no direction, there is no two-dimensional. Basically, it's just a constant for simplicity's sake as far as the math. Scalar, just a constant. Okay, if I want to triple v, it's as easy as, oh hey, it used to have a length of, well, I don't know what it is, but I'm going to call that 1 unit, and tripling it just makes it 3 times as great. So if someone says something like, hey, double the force, like if you're pulling on something, oh, come on, work twice as hard. Okay, then you could double the force by making the magnitude twice as strong. If length stands for how strong something is, we just need to make it 3 times stronger than it was before. So I have 1, I have 2, I have 3. If I were to double it, it'd be twice as long. If I were to triple it, it's 3 times as long. So, in geometry, it might not seem that big a deal as far as like, okay, whatever, just triple it. Now, here's something crazy. What if it was to have like a negative? Well, now we'd have to not only triple it, but also take away that and make it point the other direction. Because it needs to be in the opposite. If we had a negative, earlier in math, hopefully a good math teacher mentioned about how negatives or subtractions or adding the opposites. Anyway, we would change the direction if there was a negative. But in components, it's as easy as, oh hey, just multiply each of his components by that number. It literally distributes. It literally distributes. No big deal. In a picture, okay, maybe you get it. Like, it's 3 times stronger, 3 times longer. Negative, okay, whatever, change the direction of it. But in math, it's like, I don't care, just distribute. Distribute to the original vector. So maybe some of you are looking over here and you're like, oh, so double u, that just means double, double. Multiply by 2. Triple v, that just means triple, triple. Now, vector addition. This is where the picture starts to get funny. what if I have, let's see, who was this guy? This was V? Yeah. What if I have V, but I also need to add a new vector U to it? Vector addition in a picture is completely impossible until, don't worry, it's an equal vector. I'm not changing his length or his angle. Until I put the 2 vectors or the 3 or the 4 or the 5 head to tail. I need them to flow into each other to figure out the overall result. That's where that roller coaster picture came in earlier. It's called head to tail. Head is like the head of the arrow. Tail is, okay, no, not the head of the arrow, the other side. Once I put 2 vectors head to tail, the overall sum is that net force that we kind of talked about earlier. That overall sum is that net force that we talked about earlier. Now, technically, the picture that I just drew, okay, to be honest, it wasn't U plus V. It was actually V plus U. And the reason I need to change that is because vector V came first, vector U came second. Now, the nice thing is in vectors, though, addition is commutative, not subtraction, never has been, never will be. But addition is commutative, like it was with numbers. Remember, vectors aren't numbers. Vectors have a horizontal and a vertical. They're much more complicated, sorry. Complex means imaginary math. Much more complicated in the sense of they're 2-dimensional. And they could be 3-dimensional, but that's in chapter 11, and we're actually skipping that chapter. But if you want to keep going in physics, go play with chapter 11 after this. It's interesting. Okay, the picture's kind of complicated. I have vector V plus U. Okay, that's U plus V. It's all right. The sum is actually this final net force of, hey, what's the overall effect? But in the math, it's super easy. Because all I got to do is just combine like terms and say, I don't care about the picture. All I gotta do is say, hey, who are the horizontal guys? Add down. You guys add. Who are the vertical guys? You guys add. If you get the components, life is easy. If you don't get the components, well, now I have a triangle to solve. However, there's a dilemma. In this picture, if I were to use law of cosines or law of sines, guys, can I figure out the magnitude of the sum with one of those formulas? If I had side and then maybe angle and then maybe side? Could I use law of cosines or law of sines to find this side? Yeah. If I have the components, I don't even have a picture. Like, what am I supposed to do to find the magnitude up here? I could use law of sines. I could use law of cosines down here. I could do something. I'm going to put law of cosines because you would have 2 sides. Well, you could find 2 sides. Wait a minute. Hold on. I don't even know how long that is or how long that is until I do what? I would need to add them. But wait, what is the length? The length is the magnitude. How do I find the magnitude? How do I find the double line thing? What formula do I need to use? Did you box it up above? Say it, Vanessa. I just pointed it out.
A squared plus B squared.
Square rooted. If I have components, some of you guys haven't made this a big deal and need to go back, need to highlight it, need to box it. This is a huge deal. If I have components, the way I can always get the length, the way I can always get the magnitude is a squared plus b squared square rooted. Pythagorean theorem. That's huge. So over here, I could maybe figure out law of sines, law of cosines. That magnitude of the resultant is what we call him, of the sum, with law of sines and law of cosines. But I would need to get the lengths first, and I can't get the lengths until I use Pythagorean theorem. But wait a minute, if I just add them, can't I do Pythagorean theorem on him? P.S. If I were you, I would write this guy down as the resultant. I gave him to you earlier, but a lot of you guys didn't write it down. This is the resultant, otherwise known as like the net force or the net change. But it's also known as the vector sum. He's huge when it comes to vector diagrams. Because we don't necessarily always care so much about the one or the other. We care about what's the overall putting them all together. And if I was to do u plus v plus w and add another vector in here, ooh, that picture would get rough. Okay, so hold on. Slow down. The problems aren't that hard. They really aren't. So let's go ahead and check out this over here on the side. The problems aren't that hard. The idea got a little weird over there because I'm doing geometry 1 second with like triangles and lines, and then I'm saying forget that. Let's do this component thing. So here we go. We have an example of going over 2, up 1, and if they don't tell you where to start, you always just start at the origin. So, whatever, going over 2, up 1, that's one vector, that's the blue guy. Then I have going over 1, up 3. Okay, cool, that's another vector, that's the green guy. If I want to add the two together, I could be super snazzy, and I could show you a sketch, and I will in a second. But guys, the math is literally as easy as what? Add the two vectors together, and what do you get? 3, 4, right? Add the x's, add the y's. It's really as easy as that. Add the x's, add the y's. If you have the components, this is nice. Wait, if it's really that nice, then what would change if I said we needed to subtract now? Yeah, 2 minus 1 and 1 minus 3. So it'd be 1 and what, Justin? You guys agree with? Mm-hmm. One person agrees with everybody else. They don't like it. Sorry. Okay, now letter C is going to take a little more work, right? So hold on. How would we double U? What would that be? Yeah, good, Sid. It's as easy as that. If I wanted to triple V, what would that be? Yeah, keep going. 3, 9. And now I need to subtract the 2. So now what do I get? One and then negative 7. We good? Okay, we're combining my terms and we're simplifying. True. Are we good all over the place? Give me a thumbs up if you're like, I'm somewhat tracking. The geometry, what would it require us to do? I'm just saying the alternative to components, okay? The alternative to components would say, okay, for vector, or for letter A, we would have to take U first, that's the blue guy, add the V, which I could do as long as I ungroup them. Sorry, let's get to. I need to translate it because I can't have them facing 2 different directions. I don't know what the overall effect is, but I can move you up, boop, boop, boop. And then I can connect to you and say, okay, I know the vector sum is after I translate you guys head to tail. It's from the very beginning initial point to the very end, the last terminal point. There we go. I could do the same thing here, except this one would be a little bit weirder because I need to do U, that's this guy, minus V. Uh-oh. So I need to, like, flip him. I need to have a minus. He needs to go in the other direction. Oh, and then wait a minute. I have to do U, and then minus V. V the other way. Okay, this would be this one. So I would be connecting from the very beginning to the very end. That would be U minus V. And this last one, oh man, this last one's going to be a beast because this last one needs 2 or double U, which I could do. I would just need to go ahead and have him be twice as long as he normally is. Twice as long. Then I need him to be 3 times as long as he normally is. 1, 2, and then another one, 3. Oh, and then wait a minute, it's minus 3V, so I would need this guy to be all grouped and face the other direction. Oh, and I would need to do U, 2U minus 3V. I almost have it. And then that is going to be the overall resultant from the very beginning to the very end of that. Now, look and see what we just did. Instead of doing all of those pictures, we said, hey, what's U's horizontals? 2. What's V's horizontal? 1. Let's put those 2 together and say, oh, hey, I'm going to go 3. And then what's U's verticals? 1. And what's V's verticals? 3. And I'm going to say, hey, I'm going to go 4. I got there, but I got there by doing little baby right triangles of each of them. And then for letter B, I got there by saying, what's U's verticals? 2. What's V's verticals? Minus 1. And so 2 minus 1, I got my overall 1 to the resultant. And I said, what's U's verticals? 1. What's V's verticals? Negative 3. Okay, 1 minus 3, I got my 2. So I got my 1 and I got my negative 2. I got there a different way. Now in the picture it looks so much more complicated. You're breaking them up into little pieces and but I'm getting these components of the overall without having to do all this geometry or all of this picture work or all this diagram work. Vector diagram, the snazzy way of putting it. This one, 2u, I would have said, hey, okay, going over 2, going over 4, and then I need to go back. Uh-oh, I need to go back. Okay, I need to go back 1. I need to go back 2. I need to go back 3. And so overall, I have 4 minus 3 is going to be that over 1 that I ended up with. And then I said, hey, I'm going to go up 2. Oh, just kidding. Nope, I'm going to go down 9. Oh, wait, 2 minus 9, that's going to be that overall negative 7. It would have been so much harder to get there, especially doing all the components, if I didn't just write it in component form and do the math. Now, once again, if I have the picture, I totally could set it up and do law of sines, law of cosines, figure out that overall length, figure out this overall length, use some crazy parallel line magic to do some, what is that angle, side, law of cosines, then get the magnitude. Or I could just have this nice little picture up here and say, I could do Pythagorean theorem if I want. I could do Pythagorean theorem if I want. I could do Pythagorean theorem if I want. There's a geometry way to do it, but there's also a component way to do it. Law of sines, law of cosines could be required, but it could also be skipped if we just did components instead. Now, I told you guys a second ago there are all these properties that technically are still applicable to vectors, and we'll come back to this if we need it, but I don't necessarily, it's in the book, you guys can see it's a table I just stole out of there. Let's keep going and do some more problems instead. I'm seeing how much time we have left and what I think would be most helpful for what I know is coming in homework. Yeah, let's keep going. Here. I mentioned a second ago that unit vectors are those guys that have a magnitude of 1, a length of 1. But they could ask us to find a unit vector with the same direction as a given vector. If you guys want to think about it, scale drawings. Scale drawings are only as good as the scale that's given to you. Meaning, if you had some sort of blueprint, but you didn't know exactly what the scale was, how much help would it be? Not much. Especially if you were given like GPS directions or a map. And it was like, oh, hey, this is how you get there. And I'm like, yeah, that's great. But this inch on the paper, what does it really mean? Is that 10 feet or is that 10 miles? Like, I need to know how far I'm going or else I'm not going to be able to really use this effectively. I need to know what the scale is. If we're trying to find a unit vector, you can kind of think about we're just trying to get the scale. We're just trying to figure out, okay, but wait a minute, what is 1 unit? Like, what does that translate to? So with this one, if I'm given a vector of 7, 5, that means I could have gone over 7, I could have gone up 5 to get to this vector from the origin. Initial point, terminal point, there we go. Wait a minute, hold on. Well, if you ever start at the origin, how easy are components, guys? Very easy, because all you gotta do is 7 minus 0, 5 minus 0. Ooh, that's no big deal. Okay, whatever. Got his components. But here's the problem. Is this a unit vector? Yes or no, and how could you check? How about Aiden? How about Nathan? Just give him a little shh. There we go. Thanks, Aiden. Aiden, help Nathan. Where are the rest of you guys? Okay, coming back. There we go. I need somebody who's going to talk to me. All right. Is this a unit vector? Yes or no? It's okay if you say you don't know yet, but how do we figure out? The 0.75. A unit vector is supposed to have a length of what? 1. Okay, can you guys just imagine this is cut into sevenths and then be like, hey, is that a length of 1? Or this is cut into fifths. Is this a length of 1? Yes or no? No. Wait a minute. Length. We can do this, guys. We can do this. What would a length of 1 be? Wouldn't it be like 1 little tick mark? Or 1 little tick mark? Is this 1? No, but what is it? It's not 7. It's not 5. A squared plus b squared. Thank you. A squared plus b squared. Magnitude. I need to know how long he is. How long is he? Pythagorean theorem. What's 7 squared plus 5 squared? 74? What goes into 74? 2 and 37. Neither of them break down. Okay, we're good. Is that 1? No. What is it in between? Come on, amazing mathematicians out there. It's about what-ish? This number. 8-ish. Good. It's between 64 and 81, yeah? It's actually 8-ish, but on the higher end towards 9-ish. But either way, not 1. True? So how do I get a unit vector of this guy? I call it u for unit. That's just me. I call it u sub v because it's the unit vector of v. And guess what you do? All you got to do is take the old horizontal and the old vertical and do exactly what you saw me do a second ago. How did I scale it back? Divide. Dun, 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 dun. Now, at that end, or to that end, we should probably make a little baby formula just because some of you are still like, wait, I just woke up. Okay, so if ever I want to find a unit vector of some sort of, I don't even know, we'll just say a v. We could do v1, whoever's old horizontal component was, over v1 over the magnitude, his old magnitude, and v2 over the magnitude. And that's it. As easy as scaling back the horizontal vertical by how big or what his old magnitude was. I need it to be a magnitude of 1. I just take his old magnitude and say, it's fine. If I divide your old magnitude by itself, then it's going to be 1. And everybody else just needs to scale back 2. And I could scale it back to be what I want. Now, as we're talking about unit vectors, there are special names for the special horizontal unit vector and special vertical unit vector. I would be a unit vector in the horizontal position, so that would be I. J would be a unit vector in the vertical position, J. And that lets us be able to basically end today with the one other way of talking about vectors. Still not magnitudes and directions, I mean, kind of, but linear combinations are another way that you might see it. If you guys see over here, if the vector w is 4, -5, and if it's starting from the origin, okay, -0, no big deal. I could write it as in components 4, -5, but there's this other notation that kind of uses these little unit horizontal vertical guys. I just want you guys not to be scared by it. If you see something like 4i minus 5j, it means the exact same thing as components. And to be honest, if I were you, I would rewrite this to look like that, because that's way easier to work with in my mind. So if we get down to this example, and if it starts to look kind of confusing, you're like, I don't know what's going on, there are i's, there are j's, it's confusing, you can just rewrite it in component form if it makes it easier. You don't have to keep it in that weird, nasty linear combination form. And you can still think things like, hey, combine like terms. Or distribute. So if you saw this vector v, 3i minus 2j, you could go ahead and say 2v is just doubling, which will be 6 vector I minus 4 vector j. But you could have also just taken your vector v and been like, I like it better with 3, -2. And you could have gotten 6 and -4 maybe that way. Or if you want to do u plus v, you could go ahead and say, hey, let's add the i's. Oh, that's an understood 1i plus 3i is 4i. And then 5 minus 2 is 3j. But you could have also just rewritten u to be 1, 5. And then done 1 plus 3 is 4, and 5 minus 2 is 3. And the unit vector, well, that's a little bit trickier. Oh, no, it's not. Steal whoever u is, which is 1. Steal his vertical also, which is 5. And divide by, where did I get root 26 from? A squared plus b squared is c squared square rooted to get c. Now, what's the one thing we didn't get to talk about? What if they give us the components, but they want the angles and the magnitudes? That's confusing. confusing. What if we're using this easier form, but they say to go back? That'll be what we talk about tomorrow, which is the last thing we need to cover before word problems. Alright guys, get as far as you can in just getting it playing with components. I'll see you later. A lot of new, just get in there and practice. Use the examples and notes in the book account. Basic vectors in so many ways, don't give up.